First, let's review the contents of the previous lesson. We learned about the critical importance of communications technology standards, about 5G standards organizations, 5G protocol releases and processes, and about the competition between 3GPP and V5G. The development of a global standard for 5G technologies will allow for a wider range of service scenarios. We know that 5G networks will not only result in new consumer applications, but will also serve customers in a range of vertical industries. Network operators will no longer just provide the pipes. They will provide new 5G services. 5G mobile internet and mobile Internet of Things will form a unified platform for consumers, vertical industries, and network operators. 5G network architecture will have to flexibly adapt to the challenges presented by differentiated service scenarios and varied customer requirements. For consumer terminals, 5G networks will have to support multiple service scenarios and make different QoS requirements for vertical industries. 5G networks must be extremely flexible. Vertical industries require different security assurances, so different services on a 5G network must be isolated from each other. Also, 5G network operators need their networks to be easy to deploy and maintain. They need O&M that has been automated based on the Internet architecture. 5G networks need to be unified and open. Cloudification makes it possible to meet these requirements. This is the main reason for developing a cloud-based network architecture. Mobile networks mainly are comprised of a radio access network, a transport network, and a core network. Each part in turn provides access, transmission, and control. The 5G core network is a next-generation core, so it is often referred to as an NGC. It consists of the signaling control plane, user forwarding plane, and other core network functions. The G-Node B connects to the control plane and user plane of the core network through, respectively, the NGC and NGU interfaces. The 5G access network is called an NG-RAN. There is only one type of physical device, the base station. A 5G base station is called a G-Node B. G-Node Bs are interconnected through XN interfaces. This transport network connects the radio access network to the core network. It is sometimes referred to as the IP backhaul network. It's responsible for exchanging data between the radio access network and the core network. 5G terminals access the 5G network through the new radio NR to implement various services. Cloud-based 5G mobile communications networks have a reconstructed network architecture. They use NFV, or Network Functions Visualization, on the core network, Cloud RAN on the radio access network, and Software-Defined Networking, or SDN, on the transport network. These new technologies allow the network to flexibly adapt to different service scenarios. They let the network better meet the requirements of 5G. These new technologies allow a single network to work for thousands of different industries. Now, let's take a look at the trend towards complete cloudification and at some of the technology used on 5G networks. The traditional core network has a chimney-style structure. Data starts at one end and travels in a straight line to the other end, like smoke traveling up a chimney. Vendors use proprietary hardware. The equipment is expensive, resources cannot be shared, software is locked into specific hardware, capacity expansion is complicated, and it takes a long time to deploy new services. 5G networks require flexible deployment. There are a wide range of service scenarios. The end-to-end arrangement or network resources that one vertical industry requires may not be appropriate for another. So, the traditional chimney-style arrangement, is not practical. Faced with the service requirements that a 5G network will have to meet, and in light of operator needs for less expensive equipment, for improving resource utilization, and for agile rollout of new services, there is only one solution: cloudification of the core network. Network functions visualization decouples the software from the hardware. Device functions are deployed using a universal infrastructure. Proprietary computing, storage, and network devices can be replaced with generic versions. Network functions are provided by the software, which improves O&M efficiency and makes the system more flexible. 5G is developing fast, and with NFV releasing the potential of 5G networks, wireless networks are moving into an age of full cloudification. Wireless networks need to process high-frequency analog signals, but these wireless signals change rapidly over time. That's why, in the 5G era, wireless base stations are divided into two parts: a centralized baseband unit, called a CU, and a distribution radio unit, called a DU. The CU processes digital baseband signals, which are not sensitive to the delay, and cloudifies the signals on the CU. The control plane and user plane are separated. Meanwhile, the RF signals, which are sensitive to delay, are processed by the DU. The CU and the DU communicate with each other through the F1 interface. This separate CU and DU signal processing is the foundation of the Huawei Cloud RAN solution. The CU uses the Huawei E9000, a server based on standard x86. The E9000 provides non-real-time baseband data processing for 5G base stations and uses virtualization technology to provide network slicing and a wide range of other services. The DU can adapt to many different coverage and installation scenarios. It provides real-time signal processing for devices like macro, micro, or indoor distribution base stations. The Cloud RAN solution allows for an on-demand deployment and intelligent slicing, and can adapt to a diverse range of services. It can handle requirements for large bandwidth, short delay, and massive connectivity. In addition, resource pooling is implemented to improve resource utilization and expand network capacity. As IT technology has developed, the traditional model, where the software was integrated into the hardware, has been gradually evolving into a system where the hardware, the software, and the applications are separated into layers. On the IP transport network, the same thing has been happening. With SDN, the network is divided into layers. It is virtualized. More importantly, the structure of the transport network has been getting simpler and simpler. The core concept behind SDN, the decoupling of control and forwarding paired with flexible, programmable software applications, is a concept borrowed from the design of PCs and mobile phones. But when this concept is applied to IP transport, it's going to create a shift in the industry, even more massive than when it was applied to PCs and phones. Cloud-based 5G core networks and cloud RANs are mainly driven by services, but cloud-based IP transport networks are mainly driven by the available technology. SDN is like having a single brain in the middle of the network, a brain that can see the big picture. It controls the traffic throughout the entire network, and this big picture view enables it to optimize the entire thing, transforming the way the network architecture works. The core technology of SDN is the decoupling of the control plane and the data plane of the network devices. This decoupling allows for more flexible control of network traffic, which in turn provides an excellent platform for new applications and for network innovation. The centralized control provided by SDN makes O&M simpler and easier. It allows for automatic scheduling and improves network utilization. SDN improves network openness through the use of APIs, greatly reducing the time required to deploy new services. SDN makes it possible to create differentiated network slices, slices based on different QoS, slices that are custom designed for the wide range of possible 5G service scenarios. "5G networks are cloud native. Using a single physical network, a wide range of custom QoS-based network slices can be rapidly created, on demand, through the use of cloud computing technologies. By keeping resources segregated, applications for a wide range of vertical industries can be supported without compromising security. 5G networks can bring countless industries together and promote integration of the digital and physical worlds. The 5G network of the future will be smarter, more agile, and more efficient. It will be an open network system based on SDN, NFV, and network slicing technologies. In this lesson, we learned about 5G network architecture and about some of the main 5G cloudification trends like NFV, Cloud RAN, and SDN. That's it for this lesson. In the next lesson, we will discuss 5G network slicing.